And hi everyone. Today's lecture that we're going to be doing is respect to the discrete Fourier transform, or the DFT. And we're going to be observing how we move from the discrete time Fourier transform, which is the DTFT, towards the DFT. So we saw basically that we could have started with the Fourier series equation in continuous time here. And we knew that the CK exponent form here represented our harmonic components was represented by this equation here in the yellow highlighted block. The Fourier series moved towards the continuous time Fourier transform, and basically once we applied these 5 limits here, we moved from the continuous time Fourier transform to the discretized time Fourier transform. The inverse transforms are basically given because this here represents our Fourier transform and this here represents our inverse Fourier transform. So applying those 5 limits, we moved from the Fourier transform here to the discrete time Fourier transform accordingly. And what we observed was that we were able to replace the continuous time t here with discretized time nt of s, where t of s being our sample time. And instead of the integral form here that we observe, we now have a summation point for the discrete samples instead. Similarly, because the transform exists, there must be an inverse transform. The same properties also do apply. One thing to note, on the other hand, for the inverse Fourier transform is that for this part here, the limits for the inverse Fourier transform are in between positive infinity and negative infinity. But for the discrete time Fourier transform, it's between positive pi and negative pi. And this is really because in discretized time, we want to be observing the signal every 2 pi cycles, because the signal repeats itself every 2 pi cycles. Now, the DTFT basically, it's still continuous, and we end up with an infinite sequence. The frequency domain basically is the continuous function, and anything that's infinite or continuous, it's kind of very hard to represent in any sort of digital hardware, because digital hardware tends to be infinite sequences. So as of such, the DTFT is still not applicable to the discrete signal processing aspect of this course. In order to make it applicable, however, one thing we can do is actually limit the number of samples. And as of such, moving from the DTFT equation here, we move towards a limited DTFT equation, where we just, instead of going between positive infinity and negative infinity, we now have a finite number of samples, where because we're starting with n equals 0 up to capital N minus 1, because the index starts at 0 and it finishes at n minus 1 index. So this is the first way of how we can limit the DTFT for it to be applicable towards DSP. The second way to do this is we actually can sample the frequency domain. And in doing so, that means we need to have an equal spacing of samples in the frequency domain. So this actually is represented by this equation here. Delta omega is equal to 2 pi divided by n, where n is the number of samples. And the reason why we use 2 pi is because, remember, that DTFT is going to repeat every 2 pi cycles. In order to get each index, however, because this is the change represented by the delta equation here, the indexes for each one of these frequency points is going to be 2 pi k divided by n, where k is going from 0 to n minus 1. So as such, the sample frequency domain will now look like this equation here instead. And you can see here how it maps towards the original DTFT form in order to do this. Now one thing to note in particular, everywhere we had capital omega is replaced by 2 pi k divided by n here accordingly. So this capital omega here is replaced by this value here, and the capital omega here is also replaced by this value here. Also, we also, instead of going between positive and negative infinity, we're now going in between a finite number sequence. So we're going to be going from n equals 0 to n minus 1 here accordingly. So as such, since the output is now going to be a function of k, the truncated DFT is actually written in this form. And because it's truncated, and we're dealing with a finite number of samples, this moves the DTFT to the actual DFT, or the discrete Fourier transform of x of n. So basically what the equation does, it moves from the discrete time domain sequence x of n into the frequency domain sequence x of k by taking each one of these samples and transforming it from time domain to frequency domain. Now one thing to note in particular, this exponent form here, we're going to have to remember that from our previous lectures that the exponent form for e minus j theta was equal to cos theta minus j sine theta, and it's going to play a very important part in this lecture, especially when we're going to be calculated for each one of the frequency components of x of n, being that in this case it will be represented as x of k. So keep in mind about this exponent component here. We're going to have to come back to it in a little bit. Now any transform that exists, that means that inverse transform must exist. So the transform exists to move from time to frequency. The inverse transform here exists to move from frequency back into time. Now the nice thing about this is that because we limit the samples, the DFT and the IDFT pair is suitable for programming. And the reason why it's suitable for programming is because these summation series here each represents a loop. So this could be the first loop and this could be the second loop, where this will be inside the second loop. Similarly for the IDFT, the same concept applies. So these pairs for the DFT is applicable because of how they are discrete and we have finite sequence lengths. And the shorthand version of writing this, when we're going to actually do the DFT, is what we refer to W of n. And W of n actually represents our exponent equation here. So that same exponent equation that we were talking about a few slides ago, we're going to have to remember that e to the power minus j theta is equal to cos theta minus j sine theta. And we're going to actually be using this to calculate W of n here. So DFT pair, instead of writing that long equation, now becomes x of k is equal to the summation series x of n, wk of n, with subscript capital N, where k goes from 0 to n minus 1. The inverse DFT is represented by this equation here. Because we represent W of n here equal to our exponent factor, this W of n is now referred to as the Twiddle factor. So for each value of k, what happens here is that we need to make sure that wk of 0, then wk of 1, wk of 2, and so forth, it multiplies by each one of the x of n components. And after we have each one of these x of n components here, we sum them up in order to get our x of k sequence accordingly. Now the DTFT is basically periodic with respect to 2 pi, because the sequence keeps on repeating every 2 pi cycles. However, the DFT, because we limit the number of samples, is going to be periodic about n. So the DTFT is periodic about 2 pi, but because we did limit the DTFT to n samples in order to form the DFT, that means the limit is going to be our period here for the DFT. So the DFT spectrum is basically going to repeat every n frequency samples. And the output frequencies are given by this equation here, which is k delta of pi is equal to k multiplied by 2 pi divided by n. And it's measured in radians. Or it can be measured in hertz if you want to say k f of s divided by n. Just remember that k starts from 0 and it goes to n minus 1. This equation here that you're observing in the green highlighted block is important for calculating what we refer to as the bin frequencies. Now the maximum bin frequency actually occurs halfway in the interval. So basically this occurs when k is equal to n divided by 2. And as such, this means that the maximum frequency bin, if we represent this by fmax, it's basically going to be half of that of the sampling frequency. So if we observe this graphically, the time domain here, we can see it's going to be 0, the first instance of t of s, the second instance of t of s, third instance going all the way up to n minus 1 t of s. But the frequency domain is going to be, because we're transforming from n to k, it's going to be 1, 2, 3, 4, all the way going up to n minus 2. N divided by 2. And then it'll just reflect back, so we'll all the way back down to n minus 2, then n minus 1, and so forth. Because the sequence is going to be symmetrical about this n divided by 2 factor here, being our maximum frequency bin. Keep in mind these values here, because these actually indicate how actually we get these sample values here. So remember, there's going to be f of s divided by n, 2f of s divided by n, and then when we hit the maximum frequency bin, it's going to be fs divided by 2. And you can see the reflection here accordingly. This 2f of s divided by n is reflected here by minus 2f of s divided by n, and similarly here with f of s divided by n. Now in the last lecture, we basically used this sequence here in order to calculate for the DTFT. Now let's actually apply the DFT to this problem. Now the first question we want to ask is what's going to be the bin frequencies? And in this case, the bin frequencies here is going to be what's our sampling frequency. So we took 5 samples in particular, and the sampling time was 0.2. These samples here were over a time period of 1. So 1 divided by 0.2 will give us 5 Hz. In order to obtain the bin frequency equation, remember that the maximum bin frequency occurs of f of s divided by 2. In this case, it will be 2.5 Hz if we do that. But if we go k multiplied by f of s on n in order to obtain each one of the bin frequencies, that means we need to get integer values. And we know in this case, capital N here is going to be 5, and k is going from 0 to n minus 1. So as such, when we calculate this and we only observe up to the maximum bin frequency, that means our bin frequencies here is going to be 0, 1, and 2 Hz respectively. If you can't remember how actually we calculate for this, go back to slide 14 in the slides and watch the bin frequency equation and apply the k and n values accordingly, and the f of s value that we just now calculated here. This actually will help you to calculate the bin frequencies for this particular example. X of n is actually our input sequence, as we know from the previous slides, that is going to just be 5 ones, because we just took 5 samples and it was a constant magnitude of 1. What we're interested in calculating for is x of k. And we basically know that x of k here, being our DFT, is given by this equation here. What we're observing here is the Twiddle factor represented by w, which is going to be this equation here accordingly as well. So it's important to remember this overall equation here for the DFT and the Twiddle factor equation as well. If we try to expand this out accordingly and we say, okay, let's calculate for x of 0, we can see very easily that we're going to have a W5 of 0, then W5 of 0, 1, then W5 of 0, 2, keep on going all the way up to W5 of 0, 4. And each one of these Twiddle factors here, that means we're going to have to calculate for them. And expanding this out, because we only calculated for x of 0, that means we're going to have to calculate up for x of 1, x of 2, x of 3, and x of 4 accordingly. And that means that we're observing this with respect to k and n going from 0 to 4. So that means we're going to have to go from W5 0 to W5 4 4. And when you actually sum that up, that means we have to calculate 25 Twiddle factor values. And in calculating for these 25 12 factor values, it tends to get quite tedious. Because that means, luckily for the DC value where k is equal to 0, it's just going to be a flat value here. Because the 12 factor will just resolve down to 1. But then when you go like 1, 2, 3, and 4, and then n equals 1, 2, 3, and 4, you can actually start seeing that if you're watching the diagonals here accordingly, the leading diagonal here, there tends to be a little bit of sign changes, but then when you actually try to map out certain similarities throughout the entire table, it gets quite complex. So it needs to be an easier way in order to do this, in order to figure out like, okay, how do we calculate for 12 factor values? So one thing to note, for any frequency component that you're trying to calculate for, the 0th value, being x of 0 here, is what referred to as our DC component. So this is always going to resolve into some steady value here, that it's not really going to have any imaginary components, it's always going to be some real component, because this is our DC value regards to the frequency equations. All the other x values on the other hand, like x of 1, x of 2, x of 3, and x of 4, is referred to as our AC components. And these AC components are also referred to as the harmonics of the signal. Now luckily for us, because the input sequence x of n was DC in nature, and it was just basically a constant value, that means we only get a value for x of naughts. So everything else, like x of 1, 2, 3, and 4, is just going to be 0. Because the original signal was just a constant value. However, if the original signal was not a constant value, x of 1, 2, 3, and 4 is going to have a real and imaginary component when we start calculating for this. So what we observe here in particular is that when we actually did the DTFT in the previous lecture, we were actually able to obtain the nice shape of the graph here accordingly. But the DFT, because it's discretized, it only actually tells us the magnitudes at each one of these bin frequencies. It can't actually give us the shape of the graph. So if we superimpose the two of them, this actually becomes a lot more evident, because the DTFT can actually detect the amplitude of the signal peaks, but the DFT can only detect the maximum signal amplitude along with the bin frequencies. So there's no shape. And in superimposing the two, it's a lot evident seeing that the DTFT zero crossings here coincide with the bin frequencies here accordingly. So the reason for this is that the DFT is actually an approximation to the DTFT, because remember we limited the DTFT down to n samples. We are moving from an infinite sequence to a finite sequence. And the insufficient samples and those bins actually gives us a somewhat poor approximation. But as we increase the number of samples that we take, the approximation gets better accordingly. So there's also a trade-off here. It means that the more samples you have, it's more accuracy, but there's more calculations to make, so the calculations take longer. And in the physical aspect of it, that means it requires more memory to store each one of these values. So you're going to have to trade off accordingly in a real-world scenario. How many samples do you need? What is your time requirement for calculating these samples? As well as how much memory do you have in order to keep on storing these values to calculate for these samples. So actually let's observe this. Instead of using a 5-point DFT, let's go to an 8-point DFT and examine the computations involved here. So an 8-point DFT means you're going to have to take 8 samples in the time domain in order to get 8 frequencies in the frequency domain. And that means that for 12 factors here, because capital N here is going to be 8, K is going to go from 0 to 7, and we apply it here into our equation accordingly. And we know basically the 12 factor equation here is going to be that nice exponent form. When we expand this accordingly, the x of 0 is going to be this, the x of 1 is going to be here, we keep on going up all the way up to x of 7. But this scales horribly, because when we start actually thinking about how many multiplications or additions are needed, each row is going to require 8 multiplications and 7 additions. And that's going to expand quite horribly when we start going up to like bigger numbers like 16 and 32 and so forth. So for this 8-point DFT, we're going to have 8 by 8 complex multiplications, because remember the 12 factors here are going to resolve into complex numbers, and 8 by 7 complex additions. So in general, any n-point DFT is going to have n squared multiplications and n multiplied by n minus 1 additions. And to give you an idea of how horribly this scales, if we did a 1024-point DFT, we're going to be doing like 1,000,000 multiplications and 1,000,000 addition computations. And this is going to take really long. This isn't practical for a real-time application. So we need to do something about this in order to reduce these amount of calculations. So this goes back to that nice 12-factor table where you actually need to sit down and watch this a little bit more in order to figure out, okay, maybe there's a pattern hidden inside here. And let's actually observe what happens when n is even. So we're going to observe this with respect to if we actually listed out all the 12 factors here vertically. So if we observe here, after we list out our 12 factors here, and we have all our calculations array for each one of these, let's actually watch this for our observations. We can see here basically that the 12 factors tend to somewhat have a symmetric property above them. And the first symmetric property is that you're going to observe here is that if we divide this row, this entire column here in half, we can see that the first half of these 12 factors here that we are observing is reflected accordingly by the second half here, but they're multiplied by -1. So W16 of 0 here can be reflected to W minus W16 of 8. So 1 and -1. Similarly, W16 of 1 here can be reflected accordingly to minus W16 of 9. So instead of positive 0.9239, we have negative 0.9239. Instead of the imaginary component here being negative, the imaginary component here is now positive. And similarly for each one of these components that you keep on going. So that means we don't need to calculate for all the components. We can just only calculate for half of them. The next property that you need to observe in particular is that these 12 factors here repeat after you x 16. So W16 of 15 here is going to be this value here, but when you do W16 of 16, it's just going to map back to W16 of 0, which is 1. So W16 of 17 will be W16 of 1. For W16 of 18, it's going to be W16 of 2 and so forth. And this is because of the periodicity property. So the first property observation that we observed here, where we split the 12 factors in half, is the symmetry property. And for the 12 factors repeating when you exceed the index here of 16 accordingly, is referred to as the periodicity property, where the 12 factors just keep on repeating themselves. So as of such, the behavior of our 12 factors here can be represented in a phasor form. And the phasor form is basically a nice shorthand version for representing our exponent equation, which is basically e to the minus j theta. Theta here is going to be 2 pi k on n. So if we expand this all back into cosine and sine, this is going to be e to the minus j theta is equal to cosine of theta minus j sine theta, where theta is equal to 2 pi k divided by n. The shorthand version of writing this is in the phasor form, and then when you actually do the calculations, you actually observe that we can actually start calculating out each one of these 12 factors. For this first 12 factor here, we can observe here that W1 of n, no matter what, is always going to be the nth root of unity. And for every 12 factor, if you try to calculate the magnitude for it accordingly, by taking the square of the real and the square of the imaginary, summing the two together and then transforming the square root, the magnitude of each one of these 12 factors is always going to be 1. And because the index is to the negative power, that means the phasor here rotates clockwise instead of anti-clockwise. So that minus sign changes the direction of rotation for the phasor. So instead, if it was positive, that means instead of this being W0 of 8A and then this being W7 of 8A, if the index of the exponent was positive, that means we'll go W0 of 8A, W1 of 8, W2 of 8, and so forth. But because the index is negative, that means we're going in the opposite direction. So we're going in a clockwise direction instead of an anti-clockwise direction. Now it's actually quite easy to derive these values here, because from the symmetry property, we only need to calculate for half of these 12 factors. So once we have W0 of 8, 1 of 8, 2 of 8, 3 of 8, and 4 of 8, it's just basically a negative reflection of each one of these. So we only need to calculate for half of them, because W0 of 8A is just 1, but W4 of 8A is minus 1. So we just use the symmetry property in order to shortcut our work and speed up the calculations regarding for the 12 factors. So if we use the behavior of the 12 factors, we actually can find the 8 values to the 8-point DFT by only calculating for 4. And what I'd like for you guys to try as practice, and we'll do this later on in a problem set, is to recalculate that first example in these slides using the 8-point DFT. And then plot it accordingly for x of k. And I want you guys to actually observe what's going to be the difference between the 5-point DFT and the 8-point DFT. So you don't actually have to comment on the result accordingly. So I'm actually going to show you like how the calculations will keep on going here for the DFT. But programmatically, this actually can be performed instead of a sequential nature into a parallel nature. And the reason for this is that this actually is a matrix operation. Now, we can separate the DFT here into a matrix operation by using this form here. Meaning that in order to solve for x of k, we can bundle all the 12 factors here into a matrix and then multiply it by the x of n values here, represented by a vector. And this we actually refer to as a block operation. And a block operation is the basis for actually doing parallel processing. Because this means that each one of these lines here, because a matrix goes by row by column, each row here by each column can actually be performed on an independent core. So let's say in this case, because we're in an 8-point DFT, and we have 8 cores, each one of those rows there can be assigned to each one of those cores, and it can be done in one cycle. Instead of trying to do this sequentially, where you want to have to wait 8 cycles accordingly. So block operations form the basis of parallel processing. And as of such, once you can figure out how to represent any one of these equations as a matrix, you actually can take advantage of this to do parallel processing accordingly for DSP. So one thing you can try is to repeat example 2 here using the block operation and see how faster it is to calculate for it. So in shortly recapping what we did, basically we had the DTFT pair, and we basically saw that there was an infinite number of time domain samples and the frequency domain was still continuous. And in order to make the DTFT practical and move it to the DFT, we actually had to truncate the number of samples that we were taking, and we sampled the frequency domain in order to perform the DFT. We also observed that the W of n factor here, referred as the 12 factors, also play an important part in calculating for the DFT. And we can take advantage of the symmetric and periodicity properties of the 12 factors in order to speed up our calculations accordingly. Our next lecture is going to be focusing on how we move from the DFT to what we refer to as the fast Fourier transform, or the FFT.